So experiment 6 consists of circuits that are intended to modify the shape of signals. So the first member of this family of different circuits that we will consider consists of the Diode Clipper. Let's see what this does and how it does what it does. So there is an alternating voltage source. We choose a sinusoidal voltage source, and this sinusoidal voltage source is applied to this circuit consisting of a resistor over here. The purpose of this resistor is to limit the current in the circuit, so it is appropriately chosen to the value given in your handout. Then we have two parallel diode circuits here. The first one is called the upper side clipper and the second one is called the lower side clipper. You can operate one of the two or the other or both or neither as you choose. Obviously operating neither of them will not yield any wave shaping action. So what we will first do is to operate one of them and leave out the other one. The way we do it is to just close this switch so that this circuit comes into play and keep this open as being left open. So now let's understand what happens. Here's how we draw the waveforms. On the input side, we have a sinusoid. This is Vi of t. When this is applied across this diode circuit and this battery voltage is set to something like say 5 volts, given that this is say 15 volts peak to peak, let's see what happens. As long as the voltage that's appearing here is lower than the battery voltage, let's say 2 volts or 3 volts, 4 volts, this diode will remain an open circuit. So the equivalent model of this circuit will be what you would see if you didn't have this diode, just this. So whatever input signal voltage is applied merely appears at the output with a voltage drop on this resistor only if this output is loaded. Otherwise, it is a 1:1 relationship between the VO of t and the VI of t. This situation prevails until this voltage, the input voltage, exceeds the battery voltage. We are assuming, of course, that the diode is ideal. If the diode is not assumed to be ideal, which obviously it is not, then we add another 0.7 cut-in voltage to the battery voltage to determine the next state of the circuit. So when this input voltage exceeds the battery voltage plus the cut-in voltage, then this diode acts as a short. So what you would see instead of the diode here is this, which simply means that the voltage across the output terminals is 5 volts. So let's start drawing the output voltage. Right, so let's see what happens to the output voltage waveform. If this was the cut-in voltage plus the battery voltage, let's say at this level, then the output voltage rises side by side with the input voltage until this point, and then levels off at VB plus 0.7. So let's ignore 0.7 in our discussion because it's obviously going to be there, and say it levels off at VB. So this is VB, and at this point the output remains at that level. However, when the input curve starts falling and lowers itself to below VB, again this diode becomes open as we showed you earlier, and the output voltage mirrors the input voltage, reflects the input voltage. So for all these rest of the time instants, where the input voltage is less than VB, all we get at the output is a copy of the input. So we will get this. This then is the upper side diode clipper. The lower side diode clipper involves another battery and a diode turned in the opposite direction, both turned in the opposite direction. So this battery is set at some VB dash, which let us say is at this level, VB dash. Clearly this is a negative voltage, and all this circuit does is best understood if we silence the upper side clipper for a while and let the lower side clipper alone to come into play. So we do that by opening this switch and closing this one. Essentially what happens now is a sort of a mirror image of whatever happened with the upper side clipper. This diode is kept off as long as the input voltage is higher than VB dash, higher than VB dash. As soon as the input voltage tries to go below VB dash, the diode turns on, becomes equivalent to a short, and VB dash is seen as the output voltage. So what we would see in the case of the lower side diode clipper would be this. Here is the input. Let's say this is VB dash. Then we would see the input copied to the output for all voltages higher than VB dash. At this point, VB dash would appear at the output and the input would not be copied. And beyond this point, when again the input rises above VB dash, we go back to copying the input to the output. This is the upper side clipper. Or positive clipper. And this is the lower side or negative clipper. With both these in hand, the only thing that's left to do is to allow both the circuits to operate simultaneously by closing both switches. We have to restore this diode over here and then we are ready to go. All that happens now is that voltages higher than VB and voltages lower than VB dash are clipped to VB and VB dash respectively. All other voltages are replicated at the output. So let's draw that waveform over here and call it a two-sided clipper. Two-sided clipper. So what you would get here is this. Even though the input goes this way. So the yellow signal is the output. and the white signal is the input for a two-sided clipper. This is the diode clipper operated with both sides functioning.
Hello students, welcome to experiment number 6, that is operational amplifiers wave shaping. In this experiment, we will discuss all kinds of wave shaping circuits like clippers, clampers, differentiator, integrators, astable and monostable multivibrators. So first in this experiment, we will look into the clippers. The clippers diagram is given in the handout and we can implement it through the circuit given in the handout. Here for this clipper we are giving an input signal from the function generator. The value for the frequency is 1 kHz, a sinusoidal signal, and the peak to peak voltage for the input signal is 15 volt. Now, as shown in the diagram, we have connected the first switch, that is AD. The switch A dash D dash is open. So the connection, the circuit basically consists of only the AD segment of that circuit. The A dash and D dash switch is open. For this part, as we can see on the function generator, there is for the positive part of the signal, there is a clipping that can be seen in this waveform. The yellow one, that is the input, and the blue one, that is the output. So we can see a slight clipping for the positive signal for the output. We can vary this clipping through the power supply. Currently we are giving a 5 volt plus minus 1 volt to the circuit. So if we will vary this, we can see the change in the waveform as we vary the voltage VB. So for as we go on increasing the voltage, the clipping is less, as we can see. And on decreasing the power supply, that is VB, we can increase the clipping for the positive part. Now we will see the clipping for the negative part by closing the switch A dash D dash and opening the switch AD. Now we can see the waveform. The negative part of the output signal is only clipped, as can be seen on this DSO. The yellow one is again the input and the blue one is the output. So we can see the clipping only for the negative part. Now we can have simultaneously positive and negative cycle clip by closing both the switches AD and A dash D dash. So we can see from the DSO waveform, we are able to observe that both the positive and the negative cycle are being clipped by this circuit. So this circuit is called a clipper. We can vary again the clipping through varying the power supply given to the circuit, that is VB and VB dash. We can have different clipping values by just changing the power supply.
with the clipper circuit, all you will need to do is to see how the clipping function varies with the changing of VB and VB dash, and observe and superpose both the input and output signals on the scope to clearly see the clipping action. You will also be able to detect the difference of 0.7 volts between theory and practice on account of the non-ideal behavior of the diodes. So that's about the diode clipper. Now we move to the diode clamper circuit. What does the clamper circuit do? Very simple. Now let's take a look. Here again we have a sinusoidal source. So this sinusoidal source is again kept at 15 volts peak to peak, 1 kilohertz as before. And what we get to see at the output is interesting. Let's start by assuming that this capacitor is uncharged. So what happens when this voltage starts rising? When this voltage starts rising, this capacitor, let's simplify the circuit first by not having a battery over here. That is to say, we will assume that VB equals 0. So there is a short here. So initially, current will flow through the capacitor and cause it to charge. The capacitor voltage is now being charged through a circuit of almost zero resistance. The only resistance that is present is minor internal resistance of the battery here, the source here, and the diode, forward resistance of the diode. So the capacitor voltage more or less stays in pace with the supply voltage, and hence this terminal is equal and opposite to this terminal, and the output remains 0. So let's just plot the input versus the output. Here is Vi of t, not written here, and the capacitor voltage rises in parallel with the input voltage up to this point. At that point, the input voltage starts going down, and in this circuit, the diode gets reverse biased and therefore opens up. Once the diode opens up, the capacitor is stuck with the high voltage that it accumulated. In the meantime, what we observe at the output is the following. We observe that until this point, the output has no voltage. The output has no voltage because the capacitor voltage and the supply voltage cancel each other. After this point, the capacitor voltage is stuck at the positive peak of the input, which is in this case 15 volts, whereas the input voltage starts falling. So at this point, because this diode is now open circuited, what you would see at the output would be a reflection of the input with the capacitor's voltage subtracted. In short, every point after this instant would show VO of t equal to Vi of t minus the fully charged capacitor voltage, which is 15 volts. You would therefore see at the output a waveform that goes down like this. Where this is the fully charged capacitor voltage. VC max, we can call it. So this is VO of t. Now, we really haven't spoken of the resistor, and honestly, as far as the argument up to this point is concerned, let us pretend in fact that the resistor is absent. Now, if the resistor is absent, the capacitor once charged, and assuming that there are no other leakages, the capacitor will stay charged forever. So while the input continues to repeat itself like this, the output would continue to repeat itself like this. So the output would remain under the input by an amount equal to the capacitor's charged capacitor voltage value forever and ever. But now suppose we change the amplitude of the input. From 15 volts we brought it down to 10 volts. Even if we did that, the input supply voltage would come down, but the capacitors would retain the charge that it accumulated earlier, and so if the input voltage went down to, let's say, something like this, the output would remain below the input voltage by the same amount as before. Like this. This is not what we want. The purpose of clamping is to force the output voltage to assume a certain DC level with respect to the input. But in this case, the DC level of the input is not adjusting itself to changes, the DC level of the output is not adjusting itself with respect to changes of the input. If we really want that to happen, we ought to really somehow give an opportunity for this capacitor to discharge, though only very slowly over several cycles of the input signal. The capacitor should be able to discharge and thereby adjust itself to large scale or large long time changes in the input signal. This is what is the purpose of having this resistor over here. Needless to say, R times C will be a reasonably large number, several times the period of the input signal, so that changes that do occur in the input cause an adjustment of the clamping level over several cycles, not immediately. Indeed, if we kept the RC very, very low, then the clamping action itself would be affected because the capacitor would keep discharging through the resistor and not allowing the diode to remain reverse biased. So that is the simple example of a clamper with no battery present or with zero battery voltage present. Now if we have a non-zero battery voltage over here, what that would do essentially, depending upon the polarity of the battery and the magnitude of the battery voltage, would be to further bias the turn-on time of this diode either positively or negatively. If you set it at a positive value, the turn-on time would be shifted upwards. If you set it to a negative value, the turn-on time would be shifted downwards. The turn-on voltage would be shifted downwards. Positive voltage here, turn-on voltage goes up. Negative voltage here, turn-on voltage goes down. And accordingly, what you would see over here is a slightly modified waveform, such as this. So that this becomes the clamping level. instead of 0. The clamping level could be made positive or negative depending upon the battery voltage that you set over here for the clamping circuit. The resistor of course remains and serves the same purpose that it did when the battery voltage was 0. So all you need to do is to exhibit the input and the output waveforms on the two channels of the oscilloscope, making sure that the output waveform at least is watched in DC mode so that the DC shift of the output is clearly seen with respect to the input. Ideally you should really put both the input and the output onto the screen in DC mode so that you can see the DC voltage difference. You might even be able to have an adjustable source over here and you can adjust that voltage and see how after a few cycles the clamping voltage readjusts itself and the waveform of the output shifts its DC position to adapt to the new battery voltage.